Hi, hello chemistry class, and welcome back to another installment of our instructional videos. And I'm going to refer to these as the interactive readers because it's using the handout. In this case, it's over chapter 2, and these are sections that are going to cover measurements and calculations. In chemistry, especially when we're doing labs and collecting data, we are taking a lot of measurements, and from those then we're going to analyze those, do some calculations, and then draw some conclusions. So we got to talk about measurements and calculations. So it's a beautiful evening here. I'm outside and surrounded by all types of wonderful matter. If you remember chapter 1, we were talking about matter. Matter is just anything that takes up volume and has a mass. So I've got beautiful surroundings here, and we're going to dive into chapter 2 and talk about measurements and calculations. Remember, you are taking notes on this, and in your notebook or on a piece of paper, you're jotting down what I tell you we need to know for this chapter, and make sure it's kind of in a nice outline form, and then take a picture of it and upload it for me to see and give you credit. And let's learn a little bit about measurements and calculations. All right, we are going to touch on the idea of scientific method. Now, the nice thing is I'm sure you've heard about the scientific method before, so we won't spend a lot of time there and just kind of touch on it. Section 2, we're going to look at units of measurement. So we're going to look at feet, meters, the metric system, the English system. We're going to be using the metric system in science class. And then we're going to be using those measurements and talking about what do we do with them, okay? And what do we do with those measurements? How do we make sure that we're using them correctly and getting the right calculation, and so forth. Why don't you pause the video right now, and in your notebook that you're going to turn into me, just answer these 2 introductory questions. They're just helpful to get you stimulated and thinking a little bit about the topics we're going to cover today. Okay, after you've done that, let's dive into something that I hope you've already are familiar a little bit with the scientific method. We have talked about this probably in every science class that you've ever been a part of. Basically, it's an accepted an approach to using your senses and what's around you in order to draw meaningful conclusions. Okay? Now, you do this naturally. This is not something that you have to really practice because you are, I think, kind of programmed that way in order to think in a scientific manner. We think logically. So, the scientific method by definition, and you should write this down, says right here, it's a logical approach. Your brain is going to think logically already, and it's a way that we're going to solve problems. This is basically what it is. It's an approach to solve problems. Okay? So, and how do we do that? We collect data. We take good educated guesses called hypothesis, and then we're going to test that hypothesis, and then we're going to come up with, and we might test it several times, and then we're going to see if that test or those tests stand the test of time and scrutiny and other people's probing, and etc. And we're going to come up then maybe with a theory that sticks. Okay? Now, like I said, you already do this. You do this a lot already. It's natural. It's not something that you really have to think about too much. Okay? When we make observations, that's usually one of the first steps we do in the scientific method. We make observations, and either they are going to be qualitative or quantitative. Write down these 2 terms on your notes, and you should know that qualitative observations are just descriptive. They talk about color, size, big, large, small, not measurements. Okay? Quality of it. It's hot, it's cold, without an actual temperature measurement. Quantitative means you've actually taken a measurement. You're using units of some type to take some form of measurement. Okay? So when you measure mass in grams, you can say something's heavy or something's light, but if you actually take a measurement, that then now is quantitative. So make sure you write that down. We love to use graphs in chemistry and science class in order to represent the data that we're collecting. And we learn a little bit about that process as we're going through a scientific experiment, okay? And a system, you should write this definition down, is a specific portion of matter in a given region of space that has been selected for study. So basically, when we say a system, the system is what you're focused on. Write it in your own words if you want to, but it's basically what you're focused on. What are you trying to focus your attention on and study? The system is what you're studying, okay? Your hypothesis needs to be stated in a way that it is measurable. So your hypothesis, when we design an experiment and you write a hypothesis, you want to make sure it's something that you can then measure, you can test. So you want a hypothesis that is testable. Please write down in your notes, a hypothesis must be testable. Okay? When you are running your experiment, you have different variables or controls. So let's make sure we understand what these are. Controls, anything that remains constant. So in your notes, just write down the word controls, and those are things that you're trying to maintain as constant as possible so that they don't affect your results. Okay? You want them to remain constant. The things that are going to change, either that you are changing, that's your independent variable, or that are going to change as a result of what you're changing, those are called your variables. So write down controls, you keep those constant. The variables are the things that are going to change. That simple. Okay? We like to either draw or design or somehow formulate a model, and that model is going to help us represent something that may be hard to understand or see. We can't see the atoms and molecules, so we make models of those to help us understand what's going on. So it's that simple. A model is an explanation of why an event occurs and how data and events are related. But it's just simple. It's a simple tool to help us understand something better. Okay? So make sure you understand that and have that in your notes. A theory is just a generalization. It's an idea based upon what? Information, data, maybe some tests that you ran. Okay? All right, just some terms that we're throwing out there. So here basically is how the scientific method is approached. It's not necessarily a linear process. There's a lot of loops to it. But usually the first thing you want to do is you want to observe. You don't need to write down this flow chart. We're just going to talk about it right now. You're going to collect data. You're going to measure things. You're going to run an experiment. You're going to talk to other people. Okay? Then from that, you are going to then hopefully draw some type of hypothesis. If this, then that. Okay? Maybe you're going to classify things or make some predictions, or you're going to organize the data in a certain way. All right? Now, your hypothesis may be true or may be false. You need to test it. So you need to design an experiment that's going to help you to test your hypothesis so that you can further make a prediction and extrapolate. Or you're going to run an experiment. You're going to maybe talk with some other people. You got to collect data. You got to measure something. Okay? From this, then, that data either is going to support your hypothesis and you can move forward, or it doesn't and you got to recycle back. And you got to circle back and alter your hypothesis and run another test and keep going through this loop until you figured out exactly what is happening with your data and what hypothesis is true. If it is true, if your data supports your hypothesis, then you can go on and try to construct a theory using more models or making further predictions or talking with other people and their results. You might publicize that and have other people criticize it and either support it or deny it based upon their findings. Okay? And you might run more tests. So it is a fluid, many times a circular process in order to lead to trying to discover what is true. Okay? All right. Let's go on to different types of units of measurement. As I mentioned, we're going to use mostly the metric system. Okay, now, I'm not going to spend a lot of time on this, but we're going to be measuring different quantities in chemistry. It's real simple here. Quantity is something that has magnitude, size, or amount. It's something you can measure, and numerically you can probably put a number on it. Okay. So what we have is, I have here a list of different measurements, and we're going to be using, like I said, the metric system. It's also called the SI measurement system, or it stands for, it's French, it's Le Système International d'Unité. It's the international system of units. Okay? And there are 7. You need to know some of these. And now by mean know, you need to have them memorized. Okay? And I'm going to tell you which ones you have to have memorized. You need to know that the SI unit for length is the meter, and we use the abbreviation M for that. The SI unit for mass is the kilogram, not the gram, the kilogram, kg. The SI unit for time is second, and the SI unit for temperature is a Kelvin, Kelvin. So we'll talk about Kelvin and how that relates to Celsius and Fahrenheit, but you need to know that the Kelvin is the temperature that we use for the standard base unit for the SI system. Okay? We are going to talk extensively about this, the amount of a substance, that is the mole, M-O-L. We're not going to get into this, electric current and luminous intensity, so you don't need to worry about that, amperes and candela. But you need to know these memorized and have it down pat without exception. Okay? You need to know those 5 SI base units. Okay? Now, those are the base units, but of course we can multiply those base units by powers of 10, and we use prefixes in order to do that. So here are some prefixes. You don't need to memorize all of these, but you've heard of a giga, right? A giga basically is 10 to the 9th. So when you say a gigabyte, that is 10 to the 9 bytes in your memory system on your computer or whatever. Okay, kilo, you're probably familiar with that. That's basically 1,000 of something. So a kilometer is 1,000 meters. Centi, you should know centi means it's 100th, 100th of something. A centimeter is 100th of a meter. So you're multiplying by 10 to the negative 2, or 100th of something. Milli, you should know that one. That's dividing by 1,000 basically. It's 1,000th, a millimeter. Okay, and we're also going to be using micro, nano, and pico, because the world of chemistry is tiny, so small. So micro, nano, and pico, and you should be aware of those. So this is 10 to the negative 6, 10 to the negative 9, and 10 to the negative 12. Okay? So these, though, those right there, those that I check marked, you need to know those. Okay? All right. One quick little note here on a couple measurements that we will be taking. You need to know the difference between mass and weight. Weight is a measure of the force that is acting on matter because gravity is pulling on it. That's weight. Mass is the amount of stuff. Okay? Mass is the amount of stuff. Mass is measured on instruments such as a balance, and weight is measured on a spring scale. But that's not hugely important. What you do need to know is mass is basically the amount of stuff in an object, and that doesn't change depending on where you take the object. You can take the object to the moon or to the earth or some other planet or top of the mountain. The amount of stuff that it has is never going to change if you haven't altered it, but the weight of it will, because the weight is dependent on the force of gravity wherever you are, earth, moon, top of the mountain, or wherever, that's acting on it. Okay? Length, we know length is just a measurement using meters. Okay? Now, using the SI base units, we can then multiply, divide using those units, and then come up with what are called derived units. It is when we multiply or divide the standard units. You need to write this down. Here are some examples of derived units down here. Some of these you already know, some of them are going to be new. I'll show you which ones you need to know. Area. Area is length times another length. It's a base unit of length times another base unit of length. Meter times meter. Square meters. That's why we call it a derived unit. Volume is length times length times length. Base times height times width, for example. That is going to be meters cubed. That's a derived unit. So you need to know area and volume. Density. Density is mass over volume. Okay, mass over volume. So mass over volume. And mass is measured in kilograms, volume is in meters cubed. So kilograms over meters cubed is a derived unit, and that's what we use for density. Molar mass, that's something we're going to be using a lot, and that is the mass over the amount of stuff, amount of substance, the number of particles basically. That's kilograms over moles. We could also talk about molar volume, which is basically going to be the volume of the substance over the number of particles. And energy, we'll talk about this a lot, and that is basically joules. That is force times length. Not that we're going to look at that. We'll save that for physics. But joules is a measurement for energy. Okay? All right. We're going to move on here. And we are going to look at our next section, section 2.3, as we look at scientific figures, scientific measurements and significant figures. Okay? Now, when we make measurements, we use certain tools to do that. A meter stick, a balance, maybe we're using a flask to measure volume, or a pipette or something like that. We use instruments to do that. Those instruments might be really precise, or they may be not so precise, okay? And when we take a measurement, we want to know if it's correct or not. So it may be accurate, or it may not be accurate at all. So we need to understand the difference between these two words, accuracy and precision. You have to write this down. Accuracy is telling you how close are you to the measurement that is correct. How close are you to the bullseye? How close are you to the correct answer? Okay? That's what accuracy means. Precision means, can you do the experiment or the test or the measurement over and over and over again and still get the same or pretty close to the same answer repetitively? That's precision. Means how close a set of measurements made in the same way are to each other. You're comparing one measurement to another measurement. You don't know if either of them are correct. You're just taking a whole bunch of measurements, and if they're all pretty close together, then your instrument is precise. You've been precise in taking that measurement. Okay? And if your measurement is correct, if you know for sure that it's correct and it is the right answer, based upon, what is it, the accepted value, then it is accurate. So there's a difference. Here's a little illustration to help you understand. If you throw a whole bunch of darts and you're trying to hit the bullseye, on this target here. You throw a whole bunch of darts. If all of your darts hit the bullseye, you have been very accurate, because you're trying to hit the bullseye. Accurate. Okay? If you throw a whole bunch of darts and they don't hit the bullseye, but they all land in a very close area, you're not accurate. Forget about accuracy. That's not going to happen. But you are precise. Okay? You've been able to repeat over and over and over and get the same results. But something's wrong with your instrument, or in this case, your throwing ability. Okay? So accuracy is how close do we get to the bullseye, to what we want, the correct answer. Precision is, were we able to do it over and over and get the same answer or close to the same answer. Now, a measurement can be accurate, okay? But if you do that measurement over and over again, you may get wild answers. In other words, you may have hit the bullseye once, but the next time it's over here and 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 over here. So in this case, you may have had one accurate measurement, but imprecise. Or it could be precise, meaning they're all in the same region, but you've totally missed the bullseye. So it could be precise, but not accurate. What you want everything to hit the bullseye or close to it, then you would be accurate and precise. So make sure you have written down in your notes those two terms and understand them. Okay? And the other thing that we want to talk about here is percentage error. Percentage error. When we take a measurement, we're going to be off. It's going to happen. Okay, it's inevitable. But how off are we? Are we way off? Are we just slightly off? To figure out how much of an error you have, we calculate something called a percentage error. It's real simple. You take your value. When we say the experimental, this is your measurement, your value, and we subtract the accepted true value, okay? The true value. And then we find out how far apart you are, and we divide by that true value, the correct answer. And we find out what that is, and then we multiply by 100 to get the percentage, okay? So that's how you find percent error. You want to write this down and be able to make that calculation, okay? There's an example in here. I would encourage you to look at the sample problem right here on your own and make sure you understand this and can follow this and have no problem with that, and then do this practice problem, okay? So you can do that on your own. You don't need to show that to me in your notes, but you do want to look at these and make sure you understand this. Now, when we take measurements, we know that our measurement is going to be correct to a certain degree. In other words, it depends on our tool. Meaning, if I have a ruler right here, this is my ruler, and I'm measuring the length of this nail, and if I zoom in really close, I can see, oh, my ruler goes, there's 6 inches. Looks like this is an inch, or maybe it's centimeter. Let's use centimeters. Centimeters. So let's say this is 6 centimeters, that's 7 centimeters. I know that this nail is at least 6 centimeters. That's guaranteed. I know that one for sure. Okay? And then I have 0.1, 0.2, 0.3. It looks like I'm pretty sure that this is more than 0.3, but it's not quite to 0.4. So when you measure, you are allowed to guess the last value. You should have certain numbers that you are pretty sure about based upon your instrument, and then your last one should be a guess. It should be in between the marks, whatever marks are given to you. In this case, we're given tenth of a centimeter. So my measurement should go out to the nearest hundredth. It looks like, well, I'm going to guess 6. Somebody else might say, no, that's going to be a 5. It's right in between the 2 marks. Somebody might say, no, it's a 7. That's okay. There's going to be slight differences in that last number. These first 2 are certain. The last one is a guess. It's a good guess. Should be a good guess, but it's still a guess. Okay? So when you take a measurement, you are allowed to guess on that last number. So we would say that this instrument is precise to the nearest hundredth of a centimeter. Okay? All right. And you'll notice here, it's kind of given us, see, we think it's 6.36, but we also know there might be some error. We might be too low, we might be too high. So plus or minus here means I might be off by a hundredth of a centimeter. So I might be too low by a hundredth, I might be too high by a hundredth. Okay? When we use a tool, we can't go past, we can't go beyond this. I can't say this is 6.367. I don't know that. This I can't guess that number. I couldn't even guess beyond that. I can only guess one number that is an estimation. So we want to count the numbers in our measurement that are part of the measurement, that are what we say are certain plus one more guess. The significant figures are the figures, the numbers in your measurement that you are certain about, plus that one more that is estimated. Those are your significant figures. Those are significant to your measurement. Okay? Important here, significant doesn't mean certain. Remember, we guessed this last number here. This last number here was a guess. But we're pretty close. We think we're pretty close. Okay? Now, when you see a measurement, we want to figure out how many figures are significant, are part of the actual measurement. How many were certain, and which one was the one that is estimated, the guess. Okay? So here's how we determine that. I know this looks really complicated at first, but it's really not that bad. Okay? So every number that is not a 0, listen carefully, every number that is not a 0 is definitely significant. It is part of the measurement. Okay? So every number, any non-zero number, okay, any non-zero number is significant. That is a guarantee. So the only thing we have to worry about is the 0. Sometimes the 0 is just there as what we call a placeholder. It's just there to move the other numbers to their right location. Sometimes, though, a 0 is significant. It is part of the measurement. Let me show you what I mean. If I write this number, 1,000, okay? Well, these 3 zeros here, maybe I only guessed to the nearest 1,000. Maybe my instrument only has marks on there of every 1,000 or so. And I can only be certain to that number right there. Well, these zeros are not part of the measurement. They're just there to push the 1 into the correct place. These are called placeholders. Okay? They are not part of the measurement. So zeros might be there just to take space in order to push a number, like 1, into the correct location that it needs to be. Okay? But if I say 1,000 and 0.50, now these zeros here are significant. They're part of the measurement. I have some instrument that is able to measure to the hundredth of whatever unit I'm talking about here. These measurements, this measurement is involving and does include those zeros right there and actually that last 0. So here are the rules. Okay, all that to say, watch. Here are the rules for zeros, and we're going to have examples on every single one. 0. When you see a 0 between any non-zero digits, like here, and here, and here, those zeros are significant. Okay? Boom. Zeros appearing in front of all non-zero digits are not significant. They are simply pushing the other numbers, the non-zero numbers, into their correct location. So these zeros here in front, those zeros in front, are not significant. They're simply placeholders. Zeros at the end of a number and to the right of the decimal point are significant. If they follow the decimal point, after the decimal point, right there, those are all part of the measurement. I'm measuring to the nearest hundredth there. So those are significant. And zeros at the end of a number but to the left of a decimal point may or may not be significant. Here's the distinction. Okay? If a 0 has not been measured or estimated but is just a placeholder, it is not significant. How will we know? A decimal point has to be there. So if I write 2,000, those zeros are just placeholders. They're not part of the measurement, not part of the certainty and the one estimated value. These are not significant. But if I put a point here, if you see a decimal point right there, that means I have measured to the nearest meter. Here I only measured to the nearest 1,000 meters, 2,000 meters. If I put a decimal point here, then all of these zeros are part of the measurement. Okay, very important. All right, I would encourage you to try these answers right here, try these practice problems right here, and see if you can determine how many significant figures there are, and you can actually refer to the rules that are given to you right there. Okay? You can do that for all of these problems here, C, D, and E, and I'll try to remember to share the answers with you in class. Okay? All right. When we're rounding, you guys know how to round, I assume. Okay? When we're rounding, anything that is 5 or bigger rounds up. Anything that is less than 5 rounds down. Okay? If you are going to add or subtract with the measurements, you can't add or subtract numbers and then have your answer be more precise than your measurements. Okay? So what you do is this. You have to make sure that you line up your numbers like this. Okay? And so when we would add these, I'll show you 25.1, and we have another measurement that is 2.03. Okay? Notice this instrument here only measures to the nearest tenth of something, tenth of a gram. This instrument measures to the nearest hundredth of a gram. But our answer cannot be more precise than our least precise measurement. So when I add these together, okay, I get 27.13. That's what your calculator will give you, or that's what you'll get if you do it on a piece of paper. But you then have to think of this and say, you know what? This right here is measured to the nearest tenth. I cannot have my answer be more precise than the nearest tenth of a gram. So I have to round this off to just 27.1. Done. Okay? That's how you add or subtract and keep in mind significant figures. Okay? When you multiply and divide, it's a little bit different. All you do is you count up the number of significant figures in the number that has the least number of sig figs, and then you make sure that your answer has that number of sig figs as well. Okay? So for example, when you multiply 3.05 right here times 8.47, okay? Oh, sorry, they're dividing it. My apologies. We're dividing this, okay? This is finding grams over milliliters, so this would be like finding the density of something, okay? So I'm dividing 3.05 divided by 8.47. This is grams, this is milliliters. We get, on our calculator, you would get 0.360094, yada, yada, yada. But your answer cannot be that precise because you only are using measurements that gave you 3 sig figs. So when you multiply and divide, you look at the number of sig figs. Okay? This has 3 significant figures. This has 3 significant figures. Your answer can only have 3 significant figures. Okay? If one of your measurements only have 2 significant figures, your measurement can only have 2 sig figs. So your answer here would have to be 0.360. If this measurement right here, let's say this measurement was not 3.05, it was just 3.1. All right? And then whatever your answer is, you'd have to round it just to the nearest hundredth here, the nearest 2 sig figs. Okay? We'll do some more practice with this in case you're not picking it up. This, I would encourage you to look at this right here, and this will show you some rules on rounding. Although it gets a little complicated, you can look at this, but I would just say if it is greater than 5, we're going to round up. If it is 4 or less, we're going to round down. Okay? Here are rules for adding and subtracting, rules for multiplication, and those just review what I just told you, but they give you some good examples. So take a moment and look at these examples here so that you understand them. Okay? All right. We are going to stop right there. I'm going to assume that you know already scientific notation. We're going to be using it a lot. If you don't, please ask me or do a little Google search on that. Look for a video that will help you with that. Okay? So, this chapter was just all about calculations and measurements so that you can accurately make your measurements, collect your data, and then do calculations with them. Okay? All right. This is going to conclude this chapter, and as always, if you've got questions, never hesitate to ask me. I would encourage you to look through some of these other sample problems here in the handout and just use that as a study. In addition, you can go down here. There's some practice problems, and there are some review questions. Okay? So you probably want to take a little time and make sure that you understand these review questions, and I'll try to remember to share the answers with you in class. Okay? All right. Till next time, keep up the good work, everybody, and as always, let me know if I can help. See you next time.